If you wanted to tell a friend exactly where to find you, you might give them a street name, an intersecting avenue, and maybe a floor number in a building. That covers your location in space. But to actually meet up, you also need to tell them when to be there. To locate anything in the universe, you need these 4 pieces of information: 3 dimensions of space, length, width, and height, and 1 dimension of time. Together, they form a simple coordinate system that we use to navigate our daily lives. For centuries, we viewed this system through a classical lens. Space was seen as an empty, rigid stage where events happen. Time was viewed as a universal clock ticking away in the background, completely independent of the stage itself. Under that set of rules, 1 second experienced by you on Earth is identical to 1 second experienced by a comet flying across the galaxy. Your movement through space has absolutely nothing to do with your passage through time. That intuitive view made perfect sense, right up until Albert Einstein realized the universe's stage isn't rigid at all. He discovered that space and time are not separate background features. Instead, they are tightly woven together into a single, flexible fabric. We call this unified continuum spacetime. Because the dimensions of space are physically bound to the dimension of time, altering one affects the other. If you change how you physically move through space, you directly alter the rate at which you experience time. To see how this works, we look at one unbreakable rule in the universe: the speed of light in a vacuum never changes. No matter how fast you are moving, light always travels at the exact same speed. Imagine a spaceship accelerating toward Mars near the speed of light. To compensate, the universe's dimensions stretch. From Earth, you see the ship squish flat, its clock ticking slowly. But inside, the astronaut feels normal. To them, you are moving fast and your clock ticks strangely. Essentially, everyone is correct about what is happening from their own point of view. Because there is no absolute clock for the entire universe, the time you experience is specific to the journey you are taking. A mathematician named Hermann Minkowski, one of Einstein's former professors, mapped these strange physical effects into a unified geometrical model. This diagram shows his model, where time acts as a literal physical direction spreading out from an observer. It treats our movement through the years just like our movement across a map. Imagine space-time as a stack of clear photographs, each representing a single moment in time. Standing still, your perspective looks straight down through the center, but moving, your perspective tilts diagonally. You slice through the stack, glimpsing multiple time layers at once. Because of this geometric tilt, 2 people can look at the exact same sequence of events and disagree on which one happened first. It reveals that the past, present, and future aren't separate stages. They are all part of one inseparable block of reality. This flexible fabric also dictates how the heaviest objects in the universe, like planets and stars, interact with everything around them. Imagine pulling a trampoline perfectly taut and placing a heavy bowling ball in the center. The ball sinks, creating a deep curved dimple, exactly what a planet does to spacetime. If you roll a marble onto that trampoline, it doesn't get pulled by an invisible force. It simply rolls in a circle because the fabric is now curved. This is the mechanism of gravity. Mass tells the spacetime fabric how to curve, and the curvature of spacetime tells mass how to move. These grand cosmic theories are actually at work in your pocket right now. The GPS navigation in your smartphone relies entirely on this math to function. GPS satellites orbit the Earth at immense speeds, floating far above the deepest part of the planet's gravitational dimple. Because they are moving so fast and experiencing less gravity than we do on the ground, their internal clocks tick slightly faster than the clock in your phone. If engineers didn't use the equations of spacetime to correct that tiny timing difference, the map on your phone would drift off by several miles in just a single day.